My name is Prithvi Shanath and I am the TA for this course, Engineering Mechanics. So we will solve some problems this week. So let's start. So this is the first problem. So the question is, compute the force in each member of the loaded cantilever truss by methods of joint. So they've asked us to compute the force in each member in the truss. So first, we need to compute the external forces at D and E from free body diagram of the truss. So first I'll draw the free body diagram. So this angle is nothing but 30. The forces here are mentioned. And here it will be reaction forces. And this side is 5 meter, this side is 5 meter. Now from the free body diagram, now this is the reference axis. Now Fx equals to 0. So what can we write? And tension is given as 80. Sorry, we need to calculate tension. It's not given in the question. So first we need to calculate tension. So for that we will compute moment about the point E. So this is A, this is B, this is C, E and D. So first what we will do is compute the moment about the point E. So we can write 5t minus of 20 into 5 minus of 30 into 10 equal to 0. So from there 5t equals to 400. So T equals to 80 kilonewton. Now we got T. Now we have to calculate the unknown reaction forces. So how can we get that? We have to use summation of Fx equals to 0 and summation of Fy equals to 0. So using this Ex, so T cos 30, that is 80 cos 30 minus of Ex equal to 0. Therefore Ex is nothing but 80 cos 30, that is equal to 69.3 kilonewton, and from Fy equal to 0, Fy is minus 30 minus 20, minus 30 minus 20, Ey is in positive direction, so plus Ey, and plus 80 sin 30 equal to 0. So Ey equal to 50 minus 80 sin 30, so that is equal to 10. So this is 10 kilonewton. So we got Ex, Ey and the tension. Now first let us consider joint A. Considering joint A, so first I'll draw this joint. Let this be AB. This is 30 kilonewton, and let this be FAC, and this angle is 60 degree. So writing Fy equal to 0, what we will get? FAB sine of 60 minus, this is 30 minus 30 equal to 0. So FAB equals to nothing but 30 sine divided by sine 60. So that is 34.64 kilonewton, and this is uh, positive, so it is tension. Now considering fx to be 0, this will be FAB cos 60 minus of FAC equal to 0. So we will write like this. I've assumed the FA so yeah, I've assumed the FAC's direction to be in the negative, so this will be minus only. Therefore FAC equals to FAB 30 sin 60 into cos 60, that is equal to 34.64 into cos 60, that is 17.32 kilonewton, and we can see from the diagram it's in negative excitation, that is it's compression, it's under compression. Now next we will consider the point joint B. So next we will consider this joint B. Considering the joint B, so this is FBD, FAB, and let this be FBC, and this angle is 60. Now similarly we'll do the same thing here. Summation of fx and fy should be 0. First we will consider fy to be 0. So minus of FBC sin 60 Now next FAB. This will also be minus of 0.866 into 34.64. So this is equal to 0. Now FBC equal to 0.866 into 34.64 by sine of 60 degree minus, so FBC is minus 34.64. So the assumed direction is for tension, so we can say that this is in compression, right? Now considering the force equilibrium in x direction, this will be FBD plus, so it's in minus 34.64 cos 60 into 2. So this is 0. FBC equal to 2 into 34.64 into half, that is equal to 34.64 again. This is not BC, this is BD. Sorry, this is BD. Yeah. So this is again 34.64 kilonewton, and this is tension. This is under tension. Now we have to consider the joint C. Considering joint C, I'll draw this joint C. Now this angle is 60, this angle is also 60. So considering fx to be 0, FAC minus plus FAC plus FCB sorry, this is CE, which we need to compute, not V. This is CE plus FBC cos 60 and this will be FCD again cos 60 equal to 0. So now Fy equal to 0 is, so this joint, this is 20 kilonewton minus 20 minus FBC this is FBC sin 60 plus FCD sin 60 equal to 0. So from here we have to calculate first CD, then substitute it in this equation for Fx. So we will do that. FCD is equal to 20 plus FBC sin 60 divided by sin 60. So FBC is nothing but 34.64 this is 57.7 kilonewton and it is under tension. Now we go back to this Fx equal to 0 equation and substitute CD and then calculate if AC from there. If AC is nothing but minus FCE minus FBC cos 60 minus FCD cos 60. So this will be FCE. So we need to find out FCE. So I'll just change these subscripts. Now AC, what is ACF? AC is, we know, 17.32 minus 17.32. BCF, BC is nothing but, it is in compression, 34.64. And this is 57.7 cos 60. So FCE this is 63.49. This is under compression. Initially we assumed it to be in tension, so it's opposite in sign, so we can say it's in compression. Now finally we need to find out the force in member DE. Now considering the joint E, so we will just do Fy equals to 0. So I'll draw this joint. EY, this is EX, this is CE. CE is in compression, so I'll draw it like this. And this is DE, which we need to find out. Let this be in tension. And this is 60 degree. So from Fy equals to 0, FDE sine 60 equals to plus EY equal to 0. Therefore we can write FDE equals to minus of EY divided by sine 60, and EY is nothing but 10 divided by sine 60, which is 11.55. So this implies that this member is under compression. Now moving on to the next problem. Here you need to determine the range of mass m over which the system is in static equilibrium. So the question is, here what we need to do is determine the range of mass m over which the system is in static equilibrium So the coefficient of static friction is given between the chord and the upper curved surface is 0.20, while that between the block and the incline is 0.40. Neglect friction at point O. Okay, so this is already mentioned. The coefficient of static friction between the chord and upper curved surface is 0.20, while that between the block and the incline is 0.40. Neglect friction at the pivot O. Now what we have to do is, first I'll draw the free body diagram of this. First I'll draw the free body diagram. This is tension. This angle is 35 degree. The mass of this rod is already mentioned in the problem, 9 kg. So this will be 9 into 9.81. This is the reaction at O, OY and OX, and this angle is 25 degree, and this length is L by 2. And this distance is L by 6. So if we consider the moment equilibrium about O, we can find out the tension which is acting on the rod, right? So minus of TA cos 35 so this will be two L by 3, this distance 2L by 3 plus 9 into 9.81 into L by 2 cos of 25 degree. So from here we can find out the TA. So I'll just rearrange this equation. So TA is cos 35, therefore TA becomes TA cos 35 to L by 3 cos of 25. So there is one more 2 here. Yeah. So this becomes 73.3 newtons. Now we've got this tension. So there are two possibilities: motion of M impends up the inclined, and another option is motion of M impends down the inclined. So case 1, motion of M impends up the incline Now T2, T1, E, beta. So T2, the tension TA is larger of the two tensions. So this can be written as 73.3 T1E. Friction coefficient is 0.20, 30°, plus 40 pi by 180°. So if we solve this, we will get T1 as 57.4 Newton. Now from free body diagram of the block, now let me draw the free body diagram of the block. So if the motion is impending upwards, the friction force should act in the downward direction, right, in the opposite direction. So it is 0.4 times the normal force. This is the normal force, this is mg, and this is the upward tension, that is 57.4. So now if we write summation of Fy equals 0, we can write N minus mg cos 40. That's it, there are no other forces in the y direction, so equal to 0, N equal to mg cos 40°. Now from Fx equal to 0, we can write this as this will be minus of 57.4 plus mg sin 40, and this will be 0.4 into mg cos 40. So this is equal to 0. Now from here I can find out mg. From here I can find out the mass. So I'll just take common. So this becomes 6.16 kg. Now there is another possibility where m impends down the motion of m impends down the incline. So again we need to draw a free body diagram. Motion of m impends down the incline TA remains the same, that is 73.3 Newton, but in this case TA is smaller as compared to the other rope, tension in the other rope. So now I need to calculate T2 so T2 has to be found out. 73.3 E 0.2 30 plus 40 into pi divided by 180 degree. So by doing this we get T2 as 93.5 newtons. Now again I need to draw the free body diagram. This time friction will act up the incline since the block is moving downwards. Again mg is acting here and this is the normal force. So again we need to consider fx, summation of fx equal to 0 and summation of fy equal to 0. So fx equal to 0 is minus 93.5 minus 0.4 plus 0.4 n, which is nothing but mg cos 40, right? And plus mg sin 40. So from here I can get the mass. This is equal to 28.3 kg. So the required range of mass is between these two limits. So the required range is 6.16 and 28.3 kgs. Now moving on to the next problem. Here we need to find out for the link OA in the horizontal position shown, determine the force P on the sliding collar which will prevent OA from rotating under the action of couple M. Neglect the mass of the moving parts. So this is question number 3. For the link OA in the horizontal position shown, determine the force P on the sliding collar which will prevent OA from rotating under the action of the couple M. Neglect the mass of the moving parts. Now what we will do, we will give a small clockwise virtual angular movement to this crank OA in the clockwise direction, and then we'll determine the resulting virtual work done by M and P. So the crank OA is given a small clockwise angular movement. In the clockwise direction, small clockwise angular movement. Now, so after giving a small clockwise movement, this is how the crank looks like. in the displaced position. So I'll draw this. This point is O, this point is A, and this point is B. Now after giving a clockwise movement, this becomes like this. So this is delta theta. This point A has moved to position A prime. So this is A. So A delta theta is delta y, right? And B has moved to this point, B prime. This is minus dx, delta x. So from this we can write delta y equals to A delta theta now. Also from this given figure, from the right angle triangle, what can we write for this link AB? We can write x square plus y square equals to b square, right, from this right angle triangle. So we can also write b square equals to x square plus y square from the right angle triangle. From the triangle. Now we just can simply differentiate this equation. So what will it be? This side will become 0 since it's a constant. 2x delta x plus 2y delta y. Therefore delta x is nothing but y by x minus, and this side is delta y. So this is the relation. Now in place of delta y I can substitute this one, right, A delta theta. So I'll do that. So delta x equals to minus y by x A delta theta. So from the equation of virtual work, what can we write? M delta theta plus P delta x equal to 0, right? And so this is M delta theta plus P delta x equal to 0. Therefore M delta theta, in place of delta x I'll substitute this. So P y by x A delta theta. So P becomes nothing but mx y A. Or x h a. So this is the force P which we were asked to find out in the question. So this is the solution. Now moving on to the next problem. So this can easily be solved. So you can try solving this problem. You can just try solving this problem. So I'll just write the question. This is question number 4. So I'll write the question. Two uniform links the two uniform links each of mass m are in the vertical plane and are connected and constrained as shown as the angle theta between the links increases with application of horizontal force P, the light rod which is connected at a as the angle so as the angle theta between the links increases with application of the horizontal force P, the light rod which is connected at A the light rod which is connected at A and passes through a pivoted collar B compresses the spring of stiffness K. If the spring is uncompressed in the position where theta equals to 0, determine the force P which will produce equilibrium at the angle theta. So this is the question. So we are asked to find out the force P which will produce equilibrium at angle theta. And it is also mentioned that as the angle theta between the link increases with the application of P, the light rod which is connected at A and passes through a pivoted collar at B compresses the spring of stiffness K. So as the angle angle theta increases, the spring is compressed. So from this figure, what can we write x as? X can be written as 2b sine theta 2, right? So x can be written as 2b sine theta 2. B sine theta by 2. Now what is the elastic potential energy then stored? It is given as V equals to half kx square, right? So I have found out x. I'll just substitute it, half k 2b sine theta 2 whole square. So this becomes 2kb square sine square theta by 2. And the datum level is considered as this at point O. So Vg will be nothing but a negative quantity, right? Because it is below the datum level. So that is minus of 2 mg b cos theta by 2. So what is this distance between OC? It is nothing but twice of x, right? That is 4b sin theta 2. OC can be written as 2 into 2b sin theta by 2 . So what is the virtual work done? It is nothing but the virtual work done by P is P delta of this distance, so 4b sin theta 2. This can be written as P to 4b cos theta 2 into half, so this cancels, so 2pb cos of theta 2 delta theta. So this is the virtual work done. Now from the equation of virtual work we can write, what can we write? So from equation so I just need to substitute all the values. So 2b pb cos theta 2 theta by 2 delta theta, ve is nothing but 2kb square. So this is delta of 2kb square sine square theta by 2 plus delta of minus 2 mg b cos theta by 2. So I just need to differentiate 2pb cos theta by 2 delta theta becomes 2kb square to 2 sine theta by 2 cos theta by 2 and half delta theta minus 2 mgb cos theta by 2, so with that becomes plus sine theta by 2 and again half comes, so this 2 gets cancelled and this 2 gets cancelled. So 2pb cos theta 2 and delta theta, here also there is a delta theta, so this I can cancel, theta 2 k b square 2 cos theta by 2 sin theta by 2 plus mg b sin theta by 2. Now I'll cancel this b. Now finally 2p, I'll divide the RHS, So finally P equal to K B sine theta by 2 plus mg tan theta by 2 with a half. So this is the force P. So we have solved 4 questions today. This was the first problem on truss. Here we had to calculate the force in each member by the methods of joints. So first this is the problem. So first what we had to do is, first we calculated the tension by calculating the moment about the point E, and from there we got tension as 80 kilonewtons, and we considered the equilibrium of the truss as whole. So summation of fx in x direction is 0 and fy is 0. By that we got the reaction forces Ex and Ey, that is the reaction forces at this point E. So then we considered the joints separately. First we considered this joint A, and similarly we applied the equilibrium equation, and then we found out the force in members AC and member AB. Now then we considered the joint B, and following the same process we found out the force in member BC as well as in member BD. And similarly we've considered this joint C and E. So these are the forces at all the members. In the next problem we had to find out the range of mass over which the system will be in static equilibrium. So this is the problem. You can read the question. So first, so there are two cases, where case one in which the motion of M is up the incline, and case 2 is when the motion of mass M is down the incline. So first we have before considering that, we have calculated the tension in the rope using the moment equilibrium about this point O. So by doing that we got tension to be 73.3 newtons. And now for case 1, when the block is moving up the incline, the friction force will act in the downwards direction, right, to prevent the motion. So we just considered this equilibrium equation in x and y direction. By doing so, we found out mass to be 6.16 kgs. Similarly, for case 2, when the motion is impending downwards, the mass is moving downwards, the frictional force has to act upwards to prevent the motion. Similarly, we've calculated the tension in the other rope by using this equation. And from considering this, we got mass to be 28.3 kgs. So this is the required range for the mass to remain in equilibrium. And this is the second last problem that we solved. You can look at the problem. So the link is in the horizontal position. We need to determine the force P on the sliding collar, which will prevent OA from rotating under the action of couple M, and we are asked to neglect the mass of the moving parts. So first what we do is give a small clockwise angular movement to the crank O. So this is how it will look in the displaced position, right? Now what can I write about delta theta? It's nothing but this distance into delta y is nothing but a into delta theta. So, and from this triangle we can write b square equals to x square plus y square, right? So we write this equation and then differentiate it, and the left hand side of this equation becomes 0 since b is constant. Now from that we get delta x, and now from the equation of virtual world we can write m delta theta plus p delta x equals to 0. Now I substitute the expression of delta x and then finally rearrange it to get the value for p. So this is the final expression for p, and this question we just now solved. So are there any doubts regarding the problems that we solved today? You can tell me if you have any doubts. So if there are no questions, we can stop here.